So with this same situation as we had before, that I just went through in the previous video, where we've got a common source circuit, and with these parameters here, and the small signal model is here. And remember, there's three ways we can find GM and R naught. We've got a VA prime here, so we would use this version to find VA or find R naught. But we can calculate these out. So what if we had a V overdrive of 1 volt? So in this case before, we had 0.2 volts, but now I want to use 1 volt. So it's a larger V overdrive. That means a larger VGS. So the transconductance, we can find it from UN Cox W over L times V overdrive. So it's 126.5 e to the minus 6 times 100 times 1. And we get, I better write a little bigger, or smaller, we get 0.01265 amps per volt for GM, transconductance. Okay, but we also need to find R naught, because the gain is equal to minus GM R naught parallel with RD. We're not changing RD there, but when we change the current, when we change V overdrive, we must be changing the current. So if we change this, we're changing the current, and that affects both GM and R naught. So we have to go back and calculate both those. So let's find the current. It's in the saturation region, so that's 1/2 UN Cox W over L times V overdrive squared. And 1 squared is just 1, so I've got 1/2 times 126.5 e to the minus 6 times 100 times 1 squared. That equals 6.325 milliamps, and that has an effect on R naught. R naught, we had VA is 25 volts per volt, so we find R naught from this equation, because we've also got an L, 1.6 microns. So R naught is equal to VA prime times L over ID prime, and ID prime is what we just got. So that's 25 volts per micron times 1.6 divided by the current, which is 0.006325, and we get a value of well, let's just do that quick here. We get a value of 25 times 1.6 divided by 0.006325 is 6324 ohms, so 6,024, and so that's going to change the value of R naught parallel with RD. So that means that R naught parallel with RD now is equal to 1 over 6324 plus 1 over 10K. So that's 3874. And that's smaller. So now we get a gain of minus GM, which is 0.01265 times 3874 minus 49 volts per volt. in that case, that did a good thing for our gain. The effect was big on the gain, but we really hammered the input resistance, or the output resistance, because this is actually equal to R out, and that could be a problem, depending which way, what it is we're trying to do, but that certainly could be an issue. But we did get more current, more gain. So what if we had W over L is 1, instead of 100, but we still have a V overdrive of 0.2 as in the original case. So now we have a transconductance is equal to 126.5 e to the minus 6 times 1 times 0.2. That equals 25.3 e to the minus 6 amps per volt. And the current now is 1/2 mu NC ox W over L V overdrive squared, and we'll get 2.53 microamps, which means that R naught will now be 25. We changed W over L, but I'm saying we changed both W and L. We changed the ratio. We did not change L. So we still have 1.6 microns, but we have this new current, 0.00253, and that's going to equal 15.8 e to the 6 ohms. So now we have a huge output resistance. What do we do to the gain? So R naught parallel with RD is equal to 1 over 15,800 plus 1 over 10K. That's 99.94, right? Very close to this value of 10K, because that high R naught will just disappear. There's another 0 there. 15. Let's see what it. No, let's see how many zeros is there. There's 1, 2, 3, 4, 1, 2, 3, 4, so 6. Yeah, so like that. Oh, one more 0. I usually would just write that with the exponent. 15.8 e to the 6. No, there's one more 0. So there's a bunch of zeros. And so now we get a gain of GM, so minus 0.0253 times 99.94. And we get a big gain of 252. What if we have a very high current? What if ID is equal to 1 milliamp, or 100 microamps, I mean, so a smaller current. That's a smaller current than we had here. No, let's see, that's larger. So we've got a V overdrive of 0.2 still. In the same UNCOX and same VT, same RD, what is the gain? Well, we need GM. Now we know that it's 2ID over V overdrive. That would be the way to calculate GM now. So that's 2 times 0.001 or 0.0002 over 0.2, and that equals 1 milliamp per volt, or 0.001 amp per volt. And what happens to R naught? Well, R naught would be 25. We're still using the same, I haven't changed L, so 1.6 still, but now we've got a different current, 0.0001, 100 microamps. So now we've got 400 k ohms. And R naught parallel with RD is 9756. I mean, it's not quite as big, but it's still very close to 10K. And our gain minus GM R naught RD in parallel will be minus 0.001 times 9956, or 9756, which is minus 9.8 volts per volt. We've had huge impacts here, right? So from this massive gain here to a much smaller gain here, there's big effects that go on as you change these things. There's a lot of interactions causing things to change. You have to recalculate a whole bunch of stuff, and it just isn't. It isn't straightforward to always guess what's going to happen. You have to figure it out. You have to calculate it or simulate it. What if we had a current of 0.75 milliamps per volt? So that's 750 microamps per volt. Microamps. That's a current. And we have an RD is equal to 10K and a gain of minus 25 volts per volt. So that's our target. What VGS do we need? And what W over L do we need? And we'll use, we'll let VDD equal 10 volts here because we need some more headroom. So we can certainly say this much. We can say that AV is minus GM R naught parallel with RD. And this is equal to minus 25, because that's the problem statement I just said. I said I want 25 volts per volt gain. So, we know the current. So we know that R naught is 25, and we're still sticking with 1.6 microns gate length. 25 times 1.6 over 0.00075. That equals 53 k ohms. Not crazy high, but that would mean that R naught parallel with RD is equal to 1 over 53k plus 1 over 10k is 8421 ohms. And we know that GM, so we've got this relationship right here, and we just found this, and we already have this, so we can solve for GM. So GM would be minus, let's just skip the sign. So we got AV over R naught parallel with RD. So that's going to be 25 over 8421, which is 0.003 amps per volt. And we know that this is also equal to the square root of 2 mu n Cox W over L times ID. So we can solve for W over L. It's plus GM squared over 2 mu NCox. Don't forget that 2 mu NCox times ID. So we've got 0.003 squared over 2 times 126.5 e to the minus 6. Because that's that value I have right up here for mu NCox W over L. And then the current, we're given it's 750 microamps. So 750 e to the minus 6. And we get a value of 47.4. That's a perfectly reasonable number. You can't let WL over L be less than 1. If it's less than 1, you've got to do something over it. So, but I also asked, what is VGS? Right? So that's a nuisance. How do we find VGS? Well, we've got the saturation equation right here. ID is 1/2 mu NCox W over L V overdrive squared, so we can solve for V overdrive. And it'll be the square root of 2 times ID over mu NCox W over L. So we'll put those numbers in. We've got 2, and we've got a current of 750 microamps, microamps, 0.0075 over 126.5. That's illegible. 126.5 e to the minus 6 times 47.4. Got all that square root. At 47.4 is that value we just got, we just calculated for W over L. And we do that, and we get a value of 0.158 volts. And VGS is, I did not leave myself enough room, is equal to V overdrive plus VT. So that's 0.158 plus the value of VT is 0.7 volts. So we must have a value of 0.858 volts. That's a DC value. That's basically the Q point is what we're talking about. That's a DC a value that we set on VGS. So we had set 0.858 volts on VGS. So what does that really mean? If I could write. Um, 0.858 volts. What does that really mean? What we're saying is that we've got this is VGS plus little vgs of t. So that would be 0.858 volts plus little vgs of t. That's the small signal, and this should be less than about 5 millivolts or so. Probably up to 10 millivolts is going to be okay, but it's got to be something small, right? So we've set that value on the gate, and then we could draw the circuit something more like this. I think I said we've got 10 volts up here, we've got 10K here, at V out, and we've got 0.858 volts DC there. That would also be the same as saying this. We've got a little VGS That's our small signal. And that's a DC. That's our AC supply. These would all be equivalent ways of writing it. They all mean the same thing. And when we zero out the DC sources, then we have let's draw that over here. That's what we mean by zeroing out the sources. We've made this one up here in the drain ground. We already had grain on the source, and we now have ground attached directly to this small signal source, Vn, which is little VGST. All the same things, and they're all working the same way. What if I said that the source is at minus 1 volt instead of ground? So now what I'm saying is we've got circuit that looks like this. So what value do we need up on here? Well, we need to have VGS at 0.858 volts. And we've got minus 1 here, so it's got to be that now we have, and that's a DC voltage, we've got to have 0.85 or 158. 0.858. Let me do it. 0.858 minus 1. 0.142. Well, let's do it the other way. Let's do it. So VG should be equal to minus 1 plus 0.858. So let me do it that way. Minus 1 plus 0.858 is minus 1.42. It may look weird, right? We've got minus 1.42 volts, and we've got 1 volt, minus 1 volt DC right here. I could have written this this way. I could have written it. In fact, that would really be the way I would usually write that. And just remember that we've got a gate and a drain and a source, and VGS is across here. That's what you've got to be able to see to find it.